Hey everyone, welcome back. Does everyone have their cones and geodesics from yesterday? Still? Great, excellent. So we're going to continue our exploration today, but I wanted to first, is the volume too high? Is it okay? Or maybe kunjam? Ah, thank you. So before we get to that though, I want to give a little bit more of a big picture of what we're looking at. I know some of you, again, how many of you have taken a course in differential geometry? Has anyone taken a course called differential geometry before? If not, that's fine. A few people have. And what about multivariable calculus? Has anyone taken multivariable calculus? Okay, so I want to try and situate this a little bit in some things you may have seen before, some of the things we talked about yesterday. So how many people have heard of curvature? Have you heard the word curvature before? Okay, so there's lots of different definitions of curvature that you might have seen, so I'm just curious if anyone's heard of it in some form. So I want to talk about curvature a little bit before we get back to geodesics. So I want to start with the curvature of a curve, a one-dimensional curve, which you might have seen if you took a course in multivariable calculus. So the key idea when you have a curve in the plane to defining its curvature is this circle right here. So at any point on a curve in the plane, you can always draw what's called the osculating circle. And that's kind of the best fit circle at that point. So this is the osculating circle of the curve above the point x. So at that point, this circle is really snugly fitting the curve. In fact, osculating, it means kissing. So it's the circle that's hugging the curve or kissing the curve perfectly. It's tangent to the curve, but it's more than just tangent. It's the perfect size to capture something about the curvature of the curve at that point. So this is sort of this is what's called the best fit circle, or the osculating circle of the curve at that point. And that circle, it's unique, and it's going to have some radius, which is denoted by that rho there. So that radius is somehow capturing the curvature of the curve at that point, x. So in particular, the curvature at x of this curve is just defined to be 1 over the radius. 1 over the radius of the osculating circle. So it's kind of inversely proportional to the size of the osculating circle. So if the osculating circle is really tiny, it's going to have a small radius, but the curve is bending really sharply, so it's going to have a big curvature. If the osculating circle is really big, it's going to have a big radius, but 1 over that big radius is going to be a very tiny amount. So the curvature is going to be very small because if the circle is really big, it's bending slowly, it's curving slowly. So that's curvature in the plane. But obviously, we also talk about curvature of surfaces. And this is something that you may or may not have seen. Sometimes in a more advanced course on multivariable calculus, you get to it. Otherwise, maybe you see it in differential geometry. But we can define the curvature of a surface in space using the idea of one-dimensional curvature of a curve. And the key idea, the connection there, is that we can take cross-sections. So if we have a surface like this saddle here in space, we can imagine lots of cross-sections, vertical cross-sections of it. And at every cross-section, we get a curve. And each of those curves, we can measure its curvature using this idea from here of the osculating circle. So, and if you take the extreme versions, so with this curve, if we give a sign to the curvature, that osculating circle, say that if it's curving up, it's positive, if it's curving down, it's negative. And if you take the most extreme values, in this case, it's this plane here is giving the most positive curvature, and this plane here is giving the most negative curvature. And these are sort of the extreme curvatures of this surface, the extreme cross-sectional curvatures. And Gauss's idea was to define the curvature of a surface as the product of these extreme curvatures. So 1 over rho 1 times 1 over rho 2. So that gives us the curvature of the surface. So this is called Gaussian curvature. And again, this is just to put what we're doing in a bit of context. If you haven't seen this before, it's a lot to digest quickly, so don't worry too much. But this is what's known as the Gaussian curvature at that point of the surface. But luckily we don't have to, if you want to calculate the curvature, you have to do a lot of calculations using this idea. But we can get an intuitive idea of curvature without all of that. So some of you might have seen this before. You might have seen surfaces of constant curvature, like the plane, the sphere is a surface of constant positive curvature, and this saddle, this kind of hyperbolic, this saddle shape here it gives us a bit of a surface of constant negative curvature. And just like we saw over here, it's negative because we have a negative curvature on this cross-section and a positive curvature on this cross-section. So we get negative curvature. But one property of curvature, so now I want to come to some things that we can easily understand even without differential geometry. And this is that we can actually detect the curvature just by looking at a triangle. And if we have a plane, any triangle you draw on the plane is going to have what as its angle sum. If we add up the angles of a triangle, what do we get in the plane? 180, right? It says it right here. But that changes if we go to another surface. If you go to a surface of positive curvature, the angle sum will kind of grow. It'll become more than 180, and you can see that the angles are kind of bulging there. As the sphere, because the sphere has positive curvature, it's causing these angles to bulge a bit, and the angle sum will always be greater than 180. If we have a surface with negative curvature, like this saddle here, it's hard to see in the picture, but the angles are going to be kind of shrunk. They're going to kind of get kind of squeezed. So we're going to always have an angle sum less than 180. So this is a more intuitive way to understand curvature, just by drawing a triangle and measuring the angle sum. If it's a surface of constant curvature, it's guaranteed to have these properties. Okay, so that's all I want to say about curvature for the time being, and now I want to come back to geodesics. So, and also talk a little about how do geodesics and curvature interact with each other. So let's recall the definition from yesterday of geodesics. So what is a geodesic? It's a maximal path that is intrinsically straight, right? So can anyone remind me what we mean by that? How do we think about that? If it's intrinsically straight, what do I mean by that? It's locally straight. If you're an ant on the surface, you're always moving forward, you're never turning left, you're never turning right. So in that sense, it's locally straight. So as an aside, this might seem, we've understood this using these ribbons, right? Using ribbons, we can create geodesics. But again, to relate it to some things you've seen in other courses, we can make this idea very precise of being locally straight. And one way to do that, again, in multivariable calculus, it comes back to this idea of an osculating circle. Even for a curve in space that's moving about in space, at any point it's going to have an osculating circle, a circle of best fit. And that circle is going to live in a plane in space. So even if a curve is moving around in three-dimensional space, at any point it's going to have an osculating plane, a plane of curvature within 3 space. And what's very interesting is that if you now come back to the idea of a ant moving along on a surface like the sphere, if you have an ant on the sphere and it's moving on some curve that's intrinsically straight, so we can put our geodesic down and just follow it, give it an initial direction, and just see where it wants to go. It'll only move straight because the ribbon can't bend. What's happening is that its osculating plane, that plane of curvature, is always going to be normal to the surface. It's always going to be normal to the tangent plane of the surface. Another way of saying that is that its unit normal vector is always going to be normal to the surface. So some of you who've done some multivariable calculus, you might even be able to calculate the unit normal vector of a curve. So this is something you can actually verify. And in the case of the sphere, can we see, using that idea, can we see why the geodesic on the sphere actually must be a great circle? We all kind of know that, and we saw it yesterday. We kind of made these geodesics and saw that they're great circles. But if we kind of believe this idea that the unit normal vector always has to be normal to the plane, to the surface, why does that force my geodesic to be a great circle? Why does it force the geodesic to divide the sphere into 2 equal parts? Does anyone have an idea? This is a bit of a tough question, and I'm going really fast, I know. But if our unit normal vector is always normal to the sphere, what does that tell us about that unit normal vector? It's always any normal vector to the sphere. It's always pointing outward, and if we go in the other direction, what is it going to hit? The center of the sphere, right? So somehow this osculating plane is always cutting the sphere through the center of the sphere. So it's going to cut it into 2 equal parts. So that's the extent of the multivariable calculus differential geometry for today. But I just want to show you that this idea of intrinsically straight can be made precise, and it aligns with other things you might have seen. But now I want to come back to the ribbon method. So for the rest of today, we'll just use ribbons to understand geodesics. Okay, so why talk about curvature? Well, remember that, so this is another thing you may have seen before. It's there on lots of YouTube videos. If you Google curvature, this is often one of the first things that comes up, which is that curvature sort of has a very, it tends to interact with geodesics in a particular way. Namely, if you have initially parallel geodesics, geodesics that are moving parallel to each other in the plane, they'll always remain parallel. Because what are the geodesics in the plane? They're the straight lines. On the other hand, on the sphere, we've seen that if you have two initially parallel geodesics, what happens to those? Well, we've seen this before. If you have, each one is going to be a great circle, and if you initially start them out parallel like this, I'm kind of giving their initial vectors as parallel, and if I follow them along, you can see that they're actually converging to each other, right? So with a positive curvature surface, your initially parallel geodesics are going to converge on a negatively curved surface. Unfortunately, I couldn't bring one in to see, but you can imagine somehow that negative curvature is going to sort of force these geodesics to move apart, to diverge. So this is often given as another characterization of curvature: analyze initially parallel geodesics. So under non-zero curvature, somehow they don't remain parallel. That non-zero curvature distorts things somehow, or bends things. So in this way, geodesics can help us explore curvature and understand curvature. So that's another aspect I want to bring in today, throughout today. So going back to the cones from yesterday, we can ask the question, how flat is the cone really? In other words, do initially parallel geodesics remain parallel on this infinite cone? Remember, my cone, although the cones you built are finite, actually, they represent infinite cones. You should imagine that this is not really a boundary, it just keeps going. So using your cones from yesterday and your geodesics from yesterday, if needed, you can build some more. Can we answer this question? Do initially parallel geodesics remain parallel on the cone? And we'll see and so let's all look at that. We can work in pairs again, because it's helpful to have a person to hold the cone while the other person follows the geodesic. And as an activity, I want to check just that. Do initially parallel geodesics remain parallel? If not, what happens to them on a cone? And but very quickly, how do we make sure the two geodesics actually start out parallel? So you need a third geodesic to act as a base geodesic. So you have to put a base geodesic in, and it helps to put some tape so it doesn't move around. Or, even with your partner, the 4 hands you have may not be enough here, because we have a lot of geodesics to manipulate. So you'll need a base geodesic, and then you can launch your two geodesics at right angles from the base. That'll guarantee they're initially parallel. And then you just have to check what happens. Do they remain parallel? Do they converge? Do they diverge? So let's do that now. Let's spend 5 minutes. So everybody get out your cones, retape them if needed. If anybody needs any supplies, raise your hand and we'll pass it out. And let's try and check what happens to initially parallel geodesics on your cone. And just raise your hand if you need any supplies. Yeah, we have tape, scissors, paper, crayons also. Meaning? Can you explain more precisely? Yeah. So, just show me actually.
Yeah. They'll diverge when.
So, are they initially parallel first?
Yeah.
Are you sure? They don't look very. Is this a geodesic they're starting? So, just check. It's not very initially parallel, right? They're already diverging a little bit here. I wouldn't say this is not quite. So, just want to tell everyone, really be careful that your geodesics are really initially parallel. Some people I noticed, they're not really starting out initially parallel. It really helps to have a third geodesic as a base from which you're launching them, and really make sure they're as close to right angles as you can get. Because they should at least start out being parallel, otherwise this won't really tell us anything. So just be careful how you start out your geodesics, how you launch them. So I want to give a little hint to people, which is that if you imagine your two geodesics are kind of starting out, are not only parallel, but very close to each other. Maybe that's one way to think about it first. Because you could imagine that they're actually the top and bottom of a fatter ribbon. Then remember that the cone is still locally flat, right? Because you made it from paper. So in some sense, these will, whatever happens as we follow this along, it's the same thing that would happen if we were to unwrap it and just do this on the flat paper, right? Nothing is going to be very different in this version than the flat version that you worked with yesterday a little bit. So if we follow these along, again, it's a little hard to do them both together, which is why it's good to tape one first or have a friend hold one down and then follow them. But in some sense, they are going to remain parallel to each other and kind of spiral down the cone or spiral up the cone together, right? As we see here. So they're kind of staying parallel. So really the only thing but the thing that can go wrong, the place where the cone is not flat, remember flat surfaces tend to preserve parallel geodesics. The place that could mess things up is what? There's one place where this cone is not really flat in the sense the curvature is not defined. What is that place? The vertex, the vertex. So really the question is, does the vertex somehow distort anything? Does it change whether these parallel geodesics remain parallel? If they're kind of both hugging each other and they're always together, then they will actually remain parallel. It's a little, again, with these models, it's a little wobbly, so it's a little hard to tell. But hopefully, by keeping them somewhat close, you can see that they really do remain parallel to each other as long as they avoid that vertex. But what if they come close to the vertex? And what if they actually hit the vertex on different sides? In other words, they kind of flank the vertex. Like what if they're parallel here, moving up the cone, but then they come to the vertex and pass it on different sides? Then what's going to happen? So that's another thing to think about and see what's going to happen. So try that out. And again, you have to be a bit careful with launching them properly and with following them properly. So you have to be a little bit precise here to really test this with this model. So do tape your base geodesic first. Remember, the base geodesic can be misleading. This circle is not a base, right? The base of the cone is not a geodesic. Remember, we saw that. So your base geodesic, for example, might look like this, right? This is actually a base geodesic, what I've put here. The base of the cone is not a geodesic. That's what we saw yesterday. So your base geodesic, you might need something like this first to tape down. And then from that, try and launch some geodesics up to the vertex and see how the vertex distorts what's happening. If you need an extra pair of hands, the volunteers and I can also help. So if you feel like you don't have enough hands between you, raise one of your hands and we can come and give you extra hands. So. And did you, any luck? Yes. Interesting, okay.
It's parallel or not.
But it seems like it's almost staying parallel. Interesting. Okay.
I'm not sure if this is considered to be intersecting.
So you started like this, it goes like this. It intersects itself, but they don't intersect each other. Yeah, so there's a self-intersection for each of them, but they don't intersect each other. So they do remain, in this case, they're...
Intersecting each other in some sense.
Okay, yes, in some sense it is, but I guess, yeah, so this is where I haven't defined parallel properly, because what I really want is a local definition of parallel, which means if you have two bugs that are moving along the two geodesics together at unit speed, say, then they're equidistant. Their distance between them never changes, so they're moving together. So the path might intersect itself, but yeah, it's not that, I mean, eventually it is self-intersecting, but we'll still call it parallel. The two things parallel to each other. So, because they remain equidistant. So, okay, that's a really nice example. Just keep that intact because I'll use it in a second. So, yes. What happened with yours?
Still seem to remain parallel.
They still seem, okay, yes. Here they seem to remain parallel. And in fact,
Yeah, but I think initially they will first diverge and then converge once again.
if they were to, yeah. So one thing that's happening here, they're together they're moving around the vertex. So if you were to open up the cone, you can see why they're remaining parallel, because it's actually just to get plane. But actually, one thing that can happen, what if they were to move on, what if they were to come up on opposite sides of this vertex? So this moves this way, this moves this way. Then what would happen to them? That's one question.
First have a negative curvature and then it will have a positive curvature.
It will come
Something like that, yeah. So are you sure it'll first have a negative curvature though?
No, it's positive.
Yeah. So, okay. So, see if anybody. Does anybody have a possible solution they want to show? We can just take a look. An idea of what happens as the cones come up, flank the vertex, and go around. What's happening to them? Has anybody seen that? Us.
So how do you say that these two are parallel?
When I try like
So, but you have to follow the geodesics and see where they go, right? So, I want to see if. Did you manage to? Okay, that's an interesting technique. That also works actually. But here, okay, so there they're staying parallel. Has anybody seen them not staying parallel? Has anybody seen the geodesics not staying parallel? Yes, can you show? Oh, actually, once, yeah, you can reconstruct that. Did you manage to get it to work? They're intersecting, and then what happens after they intersect?
Again, when it comes on front,
Okay, okay. So, did yours work out? The
yeah, that's the base.
that's the base. Okay.
Yeah, that's like something like this.
Okay, okay. But the only thing here is that they're not being launched. Okay, but that's okay. They're at least being launched at the same angle from the base. So that's kind of okay. And then, okay, but they're going off in that direction. Okay. So they're not. Okay, great. Let's see. So in that case, they will stay parallel because they're moving together around the vertex. So the vertex isn't coming between them. So really, we want to see what happens when the vertex comes between them. So here, okay, but here they are still staying parallel, and it's a little, yeah, it's a little too hard to see what's happening there. That's right. That's right. That's a good example, though. Okay, so, okay, so I think what we're seeing is actually that most people are seeing them staying parallel because most people aren't having the geodesics actually, the vertex isn't coming between the geodesics. As long as the geodesics stay together, they will have to stay parallel. And one way to see that is to cut open your cone. And if you flatten it out, then on that flat paper, the parallel lines will stay parallel, right? Because on the plane, that's what happens. And even if it passes through that cut line, somehow they still stay parallel because we're really just moving to the other cut line together. So the thing that is a little bit more mysterious, though, is what happens when the vertex comes between the geodesics. So if the geodesics are moving up the cone together and the vertex is coming between them, then what happens to them in that case? So did anybody manage to get that to work and see what happens? What happens in that case? So maybe let's see that model. Can you can come. You can come. Yeah. So I guess one of your geodesics is white, so it's a little bit hard to see. But okay. So what's happening here? But here you weren't actually, okay, sorry. You have to remember to be very careful to follow the geodesic and let it go where it wants to go. So in this case, you've kind of twisted it. Okay, so it's not quite a geodesic in that case. Okay, so I think this is actually very hard to pull off with these models, I'm realizing. It helps to have thicker paper. So if you have slightly thicker paper like this, then it's a little bit easier to see what's going on. So maybe, could I get one volunteer to come and help me? Or maybe Namrata, you can help. So if you hold this, you can come up. So if you hold the cone here, and if we kind of follow these geodesics along, and if we let them, so what happens initially if they go is that they actually cross each other initially, right? When they go around the cone. And what you'll see happening is that if the vertex comes between them, they're going to each kind of curve around in different directions and cross each other. And then when they come back to this side of the cone, what happens with most of the cones you've been working with is that they should end up diverging, actually. I mean, they'll kind of curve together, cross each other, and then leave each other. So in some sense, the vertex acts as concentrated positive curvature. So that's, yeah, unfortunately, I think I'm realizing this paper might be a little bit too weak, so it's hard to follow the geodesics along it. But with slightly thicker paper, you can see that this vertex, it kind of acts like a concentrated amount of positive curvature that pulls these geodesics together, and then, so that they actually converge. And obviously, if two things converge, they'll eventually cross and kind of leave each other. So really, it's acting like concentrated positive curvature. Does that, thanks, Namrata. Does that make sense? In theory, I know it was a little hard to pull off with this, but is that kind of making sense? You can kind of see how that might happen. If you imagine two things, these two geodesics moving up the cone, but the vertex coming between them, they are going to curve in different ways around the vertex. They're going to cross each other, and then what you'll end up seeing most of the time, for most of you, is that they will kind of cross each other and then just keep moving apart from each other. But the weird thing is that that's not always what happens. So I know at least one of you, I know Varsha had an example where something else happened. Do you still have that available? Okay. So interestingly, that doesn't always happen. Sometimes something very strange happens with some of the cones, which is that they'll actually stay parallel, even when the vertex comes between them. Even when all of that concentrated curvature pulls them together, somehow they'll still stay parallel to each other and they won't actually cross each other. So this is something that we'll have a chance to see in a little bit, but right now I want to move on a little. But basically, in some sense, this is a bit of a trick question because not all of you are going to get the same answer because not all of you have the same cones, right? Not all cones are created equal. And the reason is that the cone angle, the angle of that paper, remember that sector that from which you're making the cone, that's going to dramatically influence the behavior of geodesics on the cone. And for certain very special cone angles, parallel geodesics are going to remain parallel. So, we'll come back to this later. Right now I want to kind of come to a simpler question because I realize this is a little bit, this idea of curvature and parallel geodesics is a little bit difficult to pull off, but we will come back to that. So let's come back to a simpler question from yesterday, which is just how many geodesics are there between 2 points on the cone? So how did we solve this question with the cylinder? What was our technique that we used yesterday with the cylinder for actually answering it? Huh. We took a cut line and we looked at not just one sheet, but you can use the mic actually.
So we took a cut line on the first point and then we used the N-sheet method to draw all possible lines.
Exactly. So we used an N-sheeted covering of the cylinder. We opened it out to get one sheet, then we added another sheet, and with each sheet we could reveal more geodesics, and we could see that there's infinitely many geodesics because we can add as many sheets as we want. Each new sheet revealed new geodesics. So let's try something similar with the cone and try and count and figure out how many geodesics there are between 2 points on a cone. And in particular, are there infinitely many or are there finitely many? And if there's finitely many, how many are there? Those are the questions we want to answer. And of course, we also would be nice to also answer how many self-intersections a geodesic will have on the cone. That was another thing that we had certain hypotheses about last time. Different people had different guesses. We saw that geodesics can self-intersect, but how many times will they self-intersect? That's another question that we'll answer now. And again, the tool we're going to use is the same tool, the N-sheeted covering. That's going to help us answer these questions. So how do we create an N-sheeted covering of a cone? So the one-sheeted covering, it's actually straightforward. It's just like we did with the cylinder, and each of you has it already with you. If you just take your cone and cut it along a cut line, along a line that goes from the vertex down to the base, then if you cut it along a straight line from the vertex to the base, that is going to let you open up your cone, and it will also, and in the process, you'll get a sector like this. So that sector is just your one-sheeted covering in this case. And like I said, unlike the cylinder, the properties of the cone are going to depend quite dramatically on the cone angle. We're going to see that the cone angle, with different cone angles, we might actually get very different behavior of geodesics on the cone. So this is an example of a 90-degree cone. The cone angle is 90 degrees. We have a point P and a point Q, let's say, and when we open it out, we actually have 2 copies of P. So as a simple experiment first, if we consider points P and Q like this, and this is a one-sheeted covering of a 90-degree cone, how many distinct geodesics can we see between P and Q based on our one-sheeted covering? 2, right? Can everyone see that there's 2 geodesics? How would we draw them if we wanted to? We could draw one from, yes, so we can call this P1, we can call this P2, and we have P1 to Q, and we have P2 to Q. So we can draw one geodesic here, and that just ends up being this one. But we can draw another geodesic from this other copy of P, right? Eventually these get merged to Q, and on the cone, that'll look something like this. It'll start out, if we're moving from P to Q, it'll start out in this direction, go around, and loop up and come here. So just from this one-sheeted covering, we can kind of draw, we can actually precisely draw 2 geodesics from P to Q on the cone. So are there any other geodesics on the cone, or are those the only 2 geodesics? Any guesses? Any guesses? Anyone else? Anyone have a guess? Are there any other geodesics between P and Q that we might be able to reveal? And now don't limit yourself to this one-sheeted covering. Suppose we're not limited to that. Maybe we can't see it in this one-sheeted covering. Are there any other geodesics that might exist between P and Q? And okay, maybe, so I know one of you is dying to say something. What might we do? The cylinder, if the one-sheeted covering wasn't enough, what did we do? We added another sheet. So feel free to add another sheet. And here's a 2-sheeted covering of the same cone. And it'll look something like this. You could actually physically make this. Rather than, this is still a 90-degree cone, but now we're wrapping around twice, right? So you'd start with a 180-degree sector and wrap it around twice to get something like this. Now we have 3 copies of P. They're all lined up here. We have 2 copies of Q. And using this, can we see any additional geodesics on the cone? Yes. So now let's call this P1, this P2, and this P3, Q1, Q2. So can anybody tell me how many geodesics can we see between P and Q now on the cone? 4. Okay. Can anybody list these? What are the 4 geodesics? So somebody raise your hand. Yes. Q1 to P1. Q1 to P2.
P3 to Q1.
P3 to Q1.
Q1 and P3 to Q2.
P3 to Q2. So is there any redundancy there? P3 to Q2? Because you said P2 to Q1, right?
Q2 to P1.
Q2 to P1, exactly. Nice, nice. So that's 4 geodesics. So like before, we actually have 6 we could draw, but there's some redundancy there. There's some repetition. Because P1 to Q1, that's the same as P2 to Q2. And P1 to Q2, that's the same as P2 to, P1 to Q, sorry. Q1 to P2, that's the same as Q2 to P3. So we have those redundancies. So there's 4 geodesics now that we can see on the cone. And hopefully you can actually, this is a construction you could actually do. You could actually start with a 180-degree cone, make sure you wrap it around twice perfectly so it lines up, and you could actually trace these geodesics and actually draw, make a cone and draw those 4 geodesics very precisely. So right now I don't want to spend too much time doing that. This is similar to what you did with the cylinder yesterday. It's a good exercise to try. But I want to ask this question. What is the total number of geodesics between P and Q? And now you can add more sheets if you want. You could add a 3rd sheet, you could add a 4th sheet. So what is the total number of geodesics going to be? So take a moment and think about this. Maybe work out with a pencil and paper. Let's take 1 minute and tell me totally how many geodesics are there? Unique geodesics will you get? This one is not, I would say do a drawing, because if you just think about it, mathematically, you might think 8. But 8 is not the correct answer, let me tell you that. So you have to work it out. So what happened in the cylinder is not quite what's happening now. Yes, so how many people, so what are some answers people have? How many people think 6 is what you said? How many people have a different answer? What is your answer? 4. So how many people think 4? Okay, how many people are still working? Okay, we'll take another 30 seconds. Okay, so are there any, I think let's talk now. Are there any answers? Are we, so again, what are, some people said 4, some people said 6. Are those the only 2 guesses, or do people have other answers? Oh, you say 5. So some people say 4, some people say 5. Any other possibilities? We're allowed to add a 3rd sheet or a 4th sheet, remember. Okay, so how many people think there's 5? Okay, how many people think there's 4? Okay, quite a few. Okay, and once again, the majority is right this time, but not always, obviously. So can anyone who said 4 tell me why we already saw 4 here. So you're saying that we don't get any additional geodesics when we add a 3rd sheet, right? If we add this 3rd sector, we're not getting any additional geodesics. And why not? Can anyone tell me? We can just give the mic to somebody. Does anybody have an explanation? What's happening? They're symmetric, you're saying?
The mirror image is same as this, so we get 4 only.
Okay, yeah, basically, yeah, maybe it's hard to explain beyond that. But, you know, if you imagine connecting this P to the different Qs, there's nothing new we get. I mean, really, we have a Q in each of the 4 sectors, and we can basically connect this P to each of those Q1, Q2, Q3, and Q4. But connecting P1 to Q3, we've already done that in some sense, right? Because connecting P1 to, Q3 will be here somewhere. Connecting P1 to Q3, that's the same thing that we got if we had connected this P to this Q, right? And connecting P1 to Q4, we've already done that as well, right? That's what we got if we connected this P to this Q. So we don't get anything new. And in some sense, you can fix your P and just think of the 4 different Qs and think about it that way. So there's only 4. There's exactly 4, and there's no more. P4 is here to Q1. Okay, so if P4 is here and we're going to Q1, is that redundant, or have we already seen that? P1 to Q2, right? This is the same as P1 to Q2. I should have given a slide with this, so you have to imagine it, but it's actually the same as P1 to Q2. That's the same as P4 to Q1. Yeah. So we have P1, P2, P3, and P4. And we have Q1 is here, Q2 is here, Q3 is here, and Q4 is here. So P1, so this is again Q1, Q2, Q3, and Q4. So P1 to Q2 is this, and we were also looking at P4 to Q1, which is this. So can everyone see that if we take this and this, they're actually giving us the same geodesic. How can we see that? When we're going from one sheet to another, actually here's an interesting point. With the cylinder, we were just translating it over. And that's how we could see which points on one sheet corresponded to points on the other sheet. We were translating that sheet over. Here, we're not translating the sheet, we're doing something else. How are we identifying these sheets with each other? What is the operation we're doing? We're not doing translation, we're doing rotation. So we're rotating about this point. So we're rotating this sector, this first sheet, to sheet 2, to sheet 3, to sheet 4. We're rotating by 90 degrees each time. And if we rotate this by 90 degrees again and again, or by minus 90 degrees, that's easier to see, we're just bringing Q1 to Q4. Oh, sorry, we're bringing P1 to P4, and we're bringing Q2 to Q1, right? So this geodesic is just getting rotated to this one. So that's why the redundancy is happening. They're really identified with each other. And yes. Sorry? A break? Huh. Yes, this is the cut. In this picture, so this is so this is the first sheet of the cone, right? So this is a cut line. These are the cut lines, but then these are copies of the cut lines. I mean, these are the. Yes. Oh, I see what you're saying. Yeah, yeah. So if you were to build this, that's a very good point. If you want to make a 4-sheeted cover physically, then you would want just like this. So this was our first sheet. This is our second sheet. This is our third. This is our fourth. And then physically, your paper would have a cut here, right? So that you could then bring this under and wrap it around and make your cone. So physically speaking, if you were to actually make a physical paper construction, here's P1, here's P4, right? And we're going to kind of slide this fourth sheet under and keep sliding until all 4 sheets coincide. So just like we did in the double version, we'll do the same thing and just slide it under and make our 4 sheets coincide and get a 4-sheeted cover that way. So that's how it would work with the 4-sheeted cover. Yeah, you would have to have a cut. Say that a little louder. Yes.
That point, let us name it as P5. So from that P5 to P1, then.
So there is no P5 actually in this case because it's a 4-sheet. We just have P1. Yeah, sorry. This is P5. You're right. I'm sorry. I made a mistake. This is P4. This is P5. That's right. So you're saying from P5 to?
P1.
To P1. To Q1.
P1. Q1.
Too good. So actually, P5 looks distinct from P1 in this picture, but actually they're the same. It's actually underneath. I've kind of distorted it just to give you a sense of, with physical paper, how you would make this. But actually speaking, this, it's not that these are actually separate. P1 is actually right on top of P5. They're really the same point. So it's just like over here. Yeah, so because at this point, and the reason that's the case is because this is exactly 90 degrees. The cone angle is exactly 90 degrees. So if we go around 90 degrees 4 times, we've come back to where we started. But this is still a very good point you're making, because what if we had a cone angle of 89 degrees? That's a good thing to consider. Suppose we had a cone angle of 89 degrees. So now we've added our 4th sheet, and we're not quite back to where we started. Now, our 4-sheeted covering does actually have a P5, which is different from P1. So now what would happen? In this case, would we get any extra geodesics? Or would we still have, how many geodesics in this case would we have? We could still connect, in this case we could have P1, so we could connect, now we can no longer quite do this, to be a bit careful here. Now we can connect P1 to Q2. We can connect P2 to Q1. Sorry, I lost my Q1. Right? We can connect P3 to Q1. Right? We can connect, sorry? P1 to Q1. Yeah, so P1 to Q1. Yes, thank you. So P1 to Q1. So we have those 4. Do we have any extras from this P5? Not really, right? So, in fact, P5 to Q2. So we have a slight problem here in that if we connect P5 to Q2, it's a little hard to see what's happening because we'll have to have another sheet to continue our geodesic. This doesn't allow us to see that geodesic very well. Remember, when we add more sheets, that's helping us follow a geodesic. Once it leaves the sheet, where does it go next? That's what we're trying to answer by adding a sheet. And in this case, we can easily see what happens if we connect P5 to Q4. We can easily see what happens how P5 connects to Q3, right? But we can't actually see what happens without adding another sheet. I mean, P5 isn't going to connect to Q2 on the existing sheet, so we'll have to add more sheets, and things are going to get a bit confusing then. And in fact, we're not going to get any new geodesics that way. So in fact, we'll still just have the same number. Okay, so I think, yeah, I hope, so maybe we can go back to the slides now. I want to move on a little bit because I still want to get to some other things before we finish. So in fact, so the two-sheeted cover shows us all the geodesics that we have. But it's actually a very good point you brought up because there's something very special about a cone angle of 90 degrees because it perfectly divides 360 degrees, right? We have exactly 4 sheets. And if we don't have a nice cone angle like that, if we have sort of an irrational or a cone angle that doesn't divide up 360 degrees nicely, we're not going to have, basically the behavior won't be as nice. We won't have, with this particular cone, almost any 2 points are going to have 4 geodesics between them. Not any 4 points, but most pairs of points. Can anyone see a counterexample here? With the 90-degree cone, are there any 2 points that don't have 4 points, 4 geodesics between them that we can see? Yeah. So there is an exception. If we have 2 points that are on this straight line, 2 points on the same radial line, those won't have. So if we have 2 radial points, we'll have, like if we have Q1 here and P1 here. We'll have 2 or 3, right? But we may not have 4. So, exactly. So we won't have as many. Yeah. Okay, so I think, and in fact, and if we don't have a cone angle that nicely divides 360, we're actually going to get different behavior on different sectors and on different portions of the cone. So I think, but rather than go deeper into that, I want to move on a little bit because we only have half an hour left. So sorry about that. But we can talk more afterwards. So one other quick question, if the cone angle were 60 degrees instead of 90 degrees, in that case, how many sheets would we have in our 6 sheets? Exactly. So we'd still loop up to where we started. We'd have 6 sheets. And how many geodesics would we have between 2 points in that case that are not radially on a radius? 6. We'd have 6 in that case. Because again, we could connect our P to the Q in any one of those sectors. That's one way to see it. Okay. So maybe a quick bonus question we could think about. How many self-intersections, if we have a 90-degree cone again, how many self-intersections can a geodesic have on this cone? Is there a limit? Yesterday we thought that there's infinitely many, but are there really infinitely many self-intersections that a geodesic can have? Using an N-sheeted covering, can we try and see more clearly how many self-intersections a geodesic can have on this cone and whether there's a limit? So let's just look at this 90-degree cone and think, how many self-intersections can a geodesic have? We've seen it physically that it can have at least 1. Can it have more than 1? So, and as a hint, if you have suppose you have some geodesic on this cone. In other words, you have some geodesic that's moving along on this cone, right? We can cut the cone and unwrap it using any cut line we want, right? We can really make any cut line to unwrap the cone. We have a choice there. We could cut we can cut from the vertex down to the base along any line. And that'll open it up and create a 90-degree sector. That'll be our first sheet. So is there any clever way of doing that? So if I have a cone and I have some geodesic along it, maybe, and I want to know how many self-intersections that geodesic has. Is there any clever cut I could do that'll help me identify how many geodesics there are? So one idea is to cut along the intersection like that. And that, if we do that, so that is one way to do it. But I want to give a slightly different way right now, which is that, a diagonal cut. We can definitely do diagonal cuts are also fine. Any line you do from the vertex down, in the end, it's going to create that first sheet. So it doesn't, it can really go at any angle, and it'll give us our first sheet. But if we do it at an angle, we can actually, so because we can change the angle, we can actually make sure that it's parallel to our geodesic in some sense. In other words, from the point of view of this first sheet, maybe your geodesic looks like this initially. And when it passes through this cut line, what's happening? Well, we have to rotate down. So it's passing through like this, but then really, it's coming back through at this angle. So it's going to come back through like this and go off like that. But it's a little confusing in this way of seeing it. But by moving our cut line, changing the angle of our cut line, we can ensure that our geodesic, at least one part of our geodesic, is parallel to the cut line. So we can ensure that our picture, in our picture, we can ensure that our geodesic starts out, is moving parallel to the cut line initially, comes up here, and then since it's a 90-degree cone, when it goes out this way, it's actually coming in this way at a 90-degree angle. So it's going to go like this. So any geodesic, we can make a cut line and make it look like this in our first sheet of our cover. So no matter how our geodesic is in our 90-degree cone, we can choose our cut line in such a way. You can imagine kind of rotating this sector and choosing it in just the right way, so that the geodesic is moving along the cut line, parallel to the cut line, through the cut line, comes in again, and moves like this. And you're just going to have that one self-intersection in that case. Over here, it'll keep going forever. Remember, it's an infinite cone, and in this direction, it'll keep going forever. So we really will only have one self-intersection for a 90-degree cone. But I'll let you guys think about how this relates to other degrees, other cone angles. So we won't do this now, but for fun, you can try on your own. Can you prove that with a 180-degree cone, you'll never have any self-intersections? And you can also think about other angles as well. So this is a more important bonus question, which is, again, coming back to this question about parallel geodesics on a cone. So like I said, in the 90-degree cone, it's kind of special in that the parallel geodesics, initially parallel, will always remain parallel. And using this n-sheeted cover, we can kind of see why that's the case. A few of you noticed that in your examples you built. And what will happen is that these geodesics, if they're parallel, you can just look at this 4-sheeted cover, which is in fact the entire Euclidean plane, and you can follow your geodesics along. And if two bugs are moving, if you imagine your geodesics as two ants walking, they begin at unit speed together, and they keep walking, they'll always remain equidistant. And in this n-sheeted covering, they'll always remain equidistant. So in some sense, this 90-degree cone is very special that way. The initially parallel geodesics will remain parallel. So, and if one of the geodesics hits a vertex, it seems like we can't really continue the geodesic beyond the vertex. But again, this 90-degree cone is very special. The 180-degree cone is also special. The 60-degree cone is also special. But if you just take a random irrational degree, it won't have this property. But with these special ones, you can continue it beyond the vertex. And again, the key is to look at the n-sheeted cover, the kind of full covering. Because what happens in the covering when a geodesic hits the vertex? So this is our first sheet of our cone. It's a 90-degree cone. Imagine your geodesic hits the vertex. if it keeps, we can actually continue it beyond the vertex. We can see where it goes next. Can anyone tell me where it goes next? So in this 90-degree cone, are you sure? Double check. That's not quite right. It's a good guess, but that's not quite right. If it hit, so imagine it's hitting, if it's coming at the cone at this, from this 45-degree angle here, it go, you know, this is another copy of the cone. It's moving across and keeps going like that. What's actually happening? It's coming back. It's bouncing back. It's bouncing back. And in fact, at any angle, that'll happen. If I come here like this and keep moving, it's still bouncing back the way it came, right? If I move up like this, it's bouncing back because this line and this segment here are the same under that rotation. So it's really just bouncing back. So with these special degrees, you can continue a cone beyond a geodesic. And it's not just a random definition, because you can also think of it as a limit. If you imagine taking a geodesic and making it closer and closer to the vertex, it's actually, if it's very close to the vertex but just avoids it, it'll just curve around and almost retrace its path. So it really will almost bounce back. So that's a good experiment to try on your own. So these are examples. When we have a cone angle of 2 pi over n, something very special is happening. And in this case, we're getting what's called an orbifold. So it's a manifold with singularities, but these singularities are surprisingly well behaved. And geodesics can be continued through the singularities, for example. So I want to spend the last few minutes on a more interesting surface, which is the tetrahedron. This is the final surface I want to consider. So maybe we can quickly pass out these sheets. Sorry, I have some sheets here. So everybody can get one of these, and we're going to quickly build some geodesics. I mean, some tetrahedra. So everybody has seen a tetrahedron before, right? It has 4 vertices. It has 4 faces. And the question I want to ask is, again, how many geodesics are there between 2 points on the tetrahedra? So don't worry about this small net here. Just cut out the big one. We're just going to use the big one right now. And just cut out the big one. And make sure you cut out the tabs as well. So keep that intact. If anybody needs a sheet, raise your hand.
Keep the flaps.
Yeah, keep the flaps. Keep the flaps. Don't lose the flaps. If you cut it out by accident, it's okay. It's not a big deal, but try and keep the flaps. So once you've cut it out, I want to first ask a question. How many geodesics are there between points P and Q? So P is the tip of the nose of the yellow lizard, and Q is the tip of the nose of the red lizard. So do fold up your tetrahedron, but don't tape it yet. Don't glue it yet. Just fold it so you can see it as a 3D tetrahedron. Maybe Bharati, you can hold it up and show. So if you fold it, you'll get a tetrahedron like this. And on that, how many geodesics are there between P, the yellow lizard's nose, to the red lizard's nose, Q? And can you find, not only how many are there, but can you see any? Ah, nice. So here's an example. And don't tape it yet, because I want to keep it, I want to be able to undo it. But again, the question is, if you start a geodesic from the yellow lizard's nose, what are the different ways you can reach the red lizard's nose? There's one easy one. There's a shortest path, right, that we can see that goes from the yellow lizard's nose to the red lizard's nose, which is just what we see there, the obvious one from P to Q. But are there other ones that you can find besides this one? Are there any other paths from the yellow lizard's nose to the red lizard's nose? So, how many people have found another path from the yellow lizard's nose to the red lizard's nose? Yeah, it's useful to crease the edges. That's good to do. But don't put any tape or glue yet. That's the only thing. But you can still crease the edges to make it fold nicely. So, does anybody have a example of a geodesic from the yellow lizard's nose to the red lizard's nose? If you go to the right, like this? Interesting. Okay, that's a really good idea. Some of you, yes, nice. So that's one. Maybe there's others as well. Okay, so I think what we'll do, let's see if we can sort of apply our strategy from before, right? So we can try and launch ribbons. That's one nice way to do it, and that's probably how you discovered this one. That's actually a very nice way. Maybe let's see this one actually first that you just described. So you were saying go from the yellow lizard's nose, but go to the right. So if this is I wish I had a bigger version now, but here's my tetrahedron, and he's saying launch it to the right like this, and you can actually see, if it's helpful to have four hands for this, but if one person holds it and you launch it, it actually ends up coming. Actually something different happens there. It actually comes back to where it started. So maybe I misunderstood you, but if you just go straight to the right like this, it actually ends up looping around and coming back to where it started, I think. So I think what will be useful here, now that everyone has these cut out, is if we can have a way of applying the same idea from before. So with the cylinder and the cone, we applied a n-sheeted covering. Can we do something similar with the tetrahedron in order to follow geodesics beyond this first sheet? Right? Everybody in your hand, you have a one-sheeted covering of the tetrahedron. When you unfold it, when you flatten it, that's giving you a first sheet, a one-sheeted covering. It folds up to the tetrahedron, but on its own, in its unfolded state, it's the first sheet of our covering. But if we can, if we can add more sheets, we can, in the flat version, still follow geodesics beyond the edge. So, for example, where does this geodesic go? We want to get geodesics from this Pali's nose to the other Pali's nose. So we have this version, this one here. But suppose we launch it in a different direction. Where does it go next? It's hard to see in the flat version, right? In the tetrahedron, we can fold it and follow it. But in the flat version, how do we see where it goes next? We need another sheet. So maybe, can anybody, I guess, so this is a one-sheeted covering. But if we have a geodesic going like this, where does it go next? So we need a second sheet. So luckily, each of you has a partner who has a second sheet. So can you arrange that second sheet in the flat version? So flatten out your tetrahedron again. And you have your first sheet. With your partner, you have a second sheet. But how would you arrange that second sheet? In order to accurately follow where the geodesic goes next. So everybody with your partner, see how that second sheet should be oriented. Nice. Yeah. Nice. Yeah. So make sure that that second sheet accurately captures where the geodesic should go next on the tetrahedron. It should capture where the geodesic is actually traveling to next in the actual 3D tetrahedron. So imagine if this sheet is folded up, where does this geodesic go next? And maybe once you have a second sheet, you could try and get a third sheet as well. No, you have to ask for permission. So if you're, yeah, so maybe you can work together. Sorry. Yeah. Um, So remember, you can't just put the second sheet in any orientation you want. The orientation is fully determined by the tetrahedron's shape. Right? There's only one place this geodesic goes next, so this has to capture that. Only 6, no more? There's no more sheets you can add? Are you sure? Okay, one group has gotten 6, thinks they've gotten 6 sheets together, but is that the limit? Is that really the most you can do? How big, with our cone we only saw a 4-sheeted covering, we couldn't do more. What's the maximum number of sheets we can put? Yes. So, nice. Okay, so since we don't have much time left, I'm going to rush us a little bit. Sorry about that. So, where does the second sheet go? I think many of you have found it. But how do we want to orient the second sheet so it accurately represents where the geodesic goes next on the tetrahedron? Well, on the tetrahedron, if you imagine it folded, where is this geodesic going next? This edge is getting identified with this edge, right? If you fold the tetrahedron, this edge and this edge are getting zipped together, right? They're getting zipped up. So this point actually is identified with this point, right? So we're kind of going into this black pulleys, into the black pulley. So it has to be rotated like this. So this is how the second sheet would be oriented. And what about the next sheet? If we want to keep following the geodesic here, the next sheet, this geodesic, this edge is getting zipped to this edge. So this is now getting identified to this point and moving this way into the red pulley. So it gets oriented like this. And we can keep going. We can keep following the geodesic and adding more and more sheets. But we can also do a different geodesic and add more sheets in a different direction. So over here we end up getting this edge and this edge are identified. They're zipped together, right? This point and this point are identified. This edge and this edge are identified. So as we move through here, we're going into the body of the yellow pulley, right? And we can keep going and keep going, right? And we can get 6, but we can go beyond that. We can keep adding more, right? So we can actually fill the plane, and there's no limit to how many sheets we can keep adding. So this is it's actually an infinite sheeted covering of the tetrahedron. For any n, we can keep adding more and more n. So now using this, can we go back to the question that I asked of how many geodesics we can find from the nose of the yellow pulley to the nose of the red pulley? So I've marked these noses. There's infinitely many, right? You can see many, many different geodesics you could draw here. And this lets us kind of classify them. And there's one per sheet, right? So you can imagine drawing these. And interestingly, we really do get a different one for every sheet. Interestingly, and this is something you have to convince yourself of, there's actually no redundancy, which is maybe a little surprising. Every one is unique. So as a final question, final question, can you find a closed geodesic on the tetrahedra from the point P to the point P? So now we want a geodesic from the tip of the nose of the yellow pulley back to the tip of the nose of the yellow pulley. And it's a closed geodesic, meaning it just loops in on itself and keeps repeating. So, and how many such geodesics can we find? So again, the n-sheeted cover is very useful for this. But since we have very little time, I'm going to, again, rush ahead a little bit. So again, I've just marked just the yellow pulley noses everywhere. How many geodesics can we find that are closed and that connect different noses of the yellow pulley? I mean, all of these, remember, there's only one yellow pulley on the tetrahedron, right? All of these are the same. So it's actually just identified with each other. So how many such geodesics can we find? So one question I have, let's just take these two, look at your 2-sheeted covering to begin with. Everyone has a 2-sheeted covering at least with their partner. So let's just take these two, this rhombus here, right? Two sheets make a rhombus. If I connect these two yellow noses, what is that geodesic doing on the tetrahedron? Can anyone tell me, just looking at this rhombus, this two-sheeted cover, the geodesic connecting this nose to this nose, what is it actually doing? It comes back, but how is it going? Can you try on your tetrahedron, can you recreate it on the 3D tetrahedron? What is it actually doing if we go from this nose to this nose? It's doing something a little bit funny, right? Because it's going through this vertex, right? This is a vertex of our tetrahedron. And it's going through that vertex, so it's behaving a little bit quirkily, right? So it's hitting the vertex, and then what is it doing? So just look at your two-sheeted cover. From that one, I'm taking this geodesic. But now let's recreate that geodesic on your tetrahedron, on your 3D tetrahedron. Tell me, what is that geodesic doing? It's actually passing through a vertex, right? And what is it doing when it hits the vertex? Is it... Sorry? It's retracing. It's bouncing back, exactly. Because this part leading up to the vertex is the same as this part after the vertex, right? Under this rotation, from this tetrahedra to the second one, those two segments are identified, right? So under that rotation, this segment here is identified with this segment here under this rotation of the first sheet to the second sheet, right? That identifies the first sheet with the second sheet. So, and on the 3D tetrahedron, your geodesic is literally just hitting the vertex and bouncing back. So it's a strange geodesic that way. But it's still a legitimate geodesic, but it's a bit strange. But what if I want to avoid geodesics that hit vertices? So the final question I want to ask is, what are all the closed geodesics on the tetrahedron that avoid vertices? So notice this one does not avoid a vertex, but in the unsheeted cover, do you see anyone? One of you mentioned this earlier. If we go straight horizontally over, that avoids vertices. So that's a geodesic that's closed, which avoids vertices. Are there any others? Go up. Go from here up to here. That also avoids vertices. So some of these geodesics do avoid vertices, but this one doesn't, right? This one here hits this other vertex. So this is not a good geodesic if we want to avoid vertices. So is there any pattern here to seeing which ones avoid vertices and which ones don't? As a little hint, I'm marking these pairs of sheets. And if we start with this one, so notice something here. If we join these two sheets together, then this sheet, this double sheet, and this double sheet, how are they related to each other? This double sheet and this double sheet. They're related by which operation? Translation, right? This sheet is rotated to this sheet. This sheet is rotated to this sheet. But together, and this sheet is rotated to this sheet. But together, these two sheets are actually translated up to this. In some sense, this is rotated here and then rotated here. First, it's rotated about this point, and then it's rotated about this point. That composition of the two rotations gives us a translation. So this double sheet is rotated to this double sheet. Translated to this double sheet. This double sheet is translated over to this. So this rhombus is translated to this rhombus, is translated to this rhombus, is translated down to this rhombus, is translated over to this. And actually, if we consider the rhombuses instead of the triangles, we get a different tessellation of the plane by rhombuses. And they're all related by translation now, not by rotation. So interestingly, all of these closed geodesics that relate this point to points in other rhombuses, to the corresponding point in other rhombuses, end up being closed geodesics on the tetrahedra, which avoid the vertices. So those give us all of those vertex avoiding geodesics on the tetrahedra. All of these other ones that connect this nose to these rotated noses are going to hit a vertex. So something very funny is going on, and it's related to something kind of deeper, which I'll end with, which is that, and by the way, there is some redundancy here, but maybe I'll skip that part. I'll let you could notice there is some redundancy here. These are all the same, but we won't worry about that right now. The rhombus tessellation, if we imagine what it's creating, it's quotienting to a torus, right? Because you can imagine this as the fundamental rhombus, all the others are copies. This edge gets identified with this edge gets identified with this edge. So topologically, it becomes a torus. And this relates to the fact that the torus is a double cover of the sphere with 4 branch points. In other words, it's a double cover of the tetrahedron. That's what we're seeing here. And all the closed geodesics on the torus descend to vertex-avoiding geodesics on the tetrahedron, which you can actually follow and build on your physical tetrahedron. So, on the torus, all of these closed geodesics, if we descend to the tetrahedron, they'll give us nice vertex-avoiding geodesics. I haven't drawn them here. And similarly, the tetrahedron is another example of an orbifold. So parallel geodesics will always remain parallel. That's another thing you can actually physically play with later if you want with your tetrahedron, once you glue them up. So that's it for the talk. Sorry for going over a little bit, but it's a fun thing to verify this with your physical tetrahedra. So I hope you take these home, eventually you glue them up, and you can actually play with the geodesics on them and actually see that 2 geodesics, as they pass through a vertex together, if they pass on opposite sides of the vertex, almost magically they'll stay parallel. It's actually a very nice thing to see. I wish I had shown that properly earlier today, but I really encourage you to try this at home. Watch and see that your geodesics will really remain parallel, even if they're going on opposite sides of a vertex. It's a very cool property. So we'll end there. I'll just mention that this is based on a painting by M.C. Escher from 1942 called Lizards. I initially tried to make these tetrahedra using the original painting, but it was made in 1942 by hand, so there's some minor imperfections. So it didn't actually perfectly match up, so that's why I made this Inkscape version that is almost the same but fixes those imperfections. It's not as beautiful as his version, but the imperfections are fixed, which lets it match up nicely. And thank you all, and if you want to learn more about these topics, here's some references I used for this study, which is, these are all very accessible books for undergraduates. I highly recommend all of these. Geometry of Surfaces by John Stilwell, Experiencing Geometry by David Henderson, Visual Differential Geometry, that's a new book by Tristan Needham, and The Symmetries of Things, which goes into orbifolds more, by Conway and Goodman Strauss and Burgiel. So thank you all, and I'll